graphical representation of the results of excess power and helium-4 measurements. For each cell, two graphs are shown, one upper and one lower, both with the same time scale. The upper one reports on the left ordinate the electric power fed into the cell for the electrolysis, and on the right ordinate we find the excess power obtained through the calibration curve of that cell and evaluated as mentioned in video number 1. The lower graph shows the measurement of helium-4 expressed in units of teraatoms, that is 10 to 12 helium atoms. There are 4 electrolysis cells and all with anode made of cylindrical platinum mesh, while the cathode is of platinum only in cell number 1 of white. In the others, the cathode consists of bundles of palladium wires in number and the diameter as shown in the table. Let's go back to the reference white cell in the upper right graph. The excess power is in the noise and similarly in the lower graph for the helium-4 measurement. The data acquisition started 200 hours before the activation of the electrolysis in the 4 cells. I remember that they are connected in series and they work in galvanostatic conditions, that is, by varying the current and not the potential difference between the anode and cathode. It's indicated for cell number 1 and also for cell number 4 the exposure interval of both to the X-ray film. The difference between the cells with the palladium cathode compared to the white cell can easily be observed also qualitatively. Heat excess versus helium-4 and apparent no-time correlation. The previous graphs, such as the one for cell 4 reproduced here, show that significant values of helium-4 often do not coincide with excess heat. It must be considered that the measurement of excess heat is almost continuous measurement. The acquisition interval is 60 seconds. The measurement of helium-4 is discontinuous. A large volume of the gaseous mixture coming from the electrolysis is not analyzed. In the experiment of about 950 hours, 382 samplings were carried out, each of 150 cubic centimeter of mixture consisting of nitrogen, deuterium, and oxygen corresponded to 5.73 10 to minus 2 cubic meters under normal conditions, to be compared with 2.24 cubic meters under normal conditions of a mixture flowed throughout the experiment. Thus, only about 2.6% of the mixture was analyzed. Helium-4 and energy balance. Time profile simulation of helium-4 from the cell to the quadruple mass spectrometer. In order to find a time correlation between the recorded excess power and the experimentally unsynchronized helium measurements, some tests were carried out to determine the helium transfer profile from a given cell to the mass spectrometer, maintaining the same operating conditions of the real experiment. The procedure consisted of injection at interval of time into one of the cells of a 10 cubic centimeter of air at the atmospheric pressure and at 20 degrees C. The input is equivalent to 1.27 10 to 15 helium atoms. The atomic fraction of helium in air is 5.24 parts per million. The helium content is measured by the quadruple mass spectrometer. The time profile accumulated by the N injection is well represented by this function. This implies that if helium were generated in equal and time-spaced events, the maximum value would be revealed at the time given by this relationship, where T0 is equal 0 in the graph. Helium-4 and the energy balance. Instantaneous generations of helium-4 and their transfer to the quadruple mass spectrometer. Having previously acquired the helium transfer profile from the cell to the mass spectrometer, we can think of a correlation model between these two quantities, excess power and helium. Thus, it's assumed that the excess power is generated at certain times Tpi, and at the times Tsi, sampling of the gaseous mixture takes place. The time required for sampling is given by this equation, which is essentially depends on the volume of the sampling cylinder, which is 150 cubic centimeter, and on the flow of the carrier, which is a nitrogen, which transfers the gaseous mixture, leaving the cell to the mass spectrometer. The nitrogen flow is constant. Delta T is therefore the minimum time window where the helium measurement is performed. The helium atoms present in the sampling volume are the sum of all the contributions of the helium formation events that occurred in the time delta T from the beginning of the sampling. The total number of helium atoms, NSI, is given by this relation. The figure schematically shows this type of reasoning. In the equation below, the summation is extended to the number of points where the excess power was measured. Since the time required for sampling is much greater than the time difference between the excess power measurements, it can be shown that the number of helium atoms is given by this equation. This QR number is the power associated with a nuclear reaction event between deuterium nuclei to generate helium-4. Helium-4 and the energy balance comparison with excess power. Through the previous correlation, it can be seen that the transition from the upper graph, which represented the experimental trend of the excess power and the measurement of helium, to the lower graph, where the time correlation between the helium and excess power is reported. As a result of the elaboration that we have done to the model, it can be seen that there is a rather significant correspondence between the excess power and the helium. The ratio of a measured helium to calculated helium is shown in this graph. It's clearly seen in the insert in the graph that basically the energy balance is satisfied within the experimental uncertainty, since this ratio is between 0 and 1. The processing of the helium measurements is congruent with the excess power, and the ratio between measured and the calculated helium is compatible with the uncertainty associated with the calculation of the diffusion of helium in the transfer from the cell to the mass spectrometer.